All right, so we're recording. Please pay attention. By the way, if you just joined us late, please pay attention to what the top of this board says. Our last class is not the 25th, it's the 23rd, and I've adjusted the correct dates for the final. So if you have questions, email me. So what we're going to do is let's look at a number. How about 25? Someone's chapping. I'd like it to be in person, Mackenzie. Yeah.
Good, because I'm bringing Oakmont Bakery.
There you go. Yeah, I mean, I normally want to be in person as long as we're loud, but we had some logistics stuff today, and so I figured why make it more difficult. So this is why. So if you're mad, I'm sorry that we're not in person. All right, look, let's take a number like 25. And in class on Monday, I talked about if you want to convert to base B, or for where B is any base, one way to do it is ask yourself, what is the largest power of that number that goes into this number? And then I showed you a couple other ways to think about it. And the one way I showed you to think about it was to do that game where we drew the dots and then we counted how many pairs of 2 there were. Now, what that was a symbolic way of repeatedly dividing by 2. So what I'd like to do is instead of using dots, I'd like to use a little more different notation. I would like to just divide this thing by 2. So if I take 25 and divide it by 2, I get 2 times 12 plus 1. And so the key thing is we want to look at 2 numbers here. We want to look at the remainder. This is important. And remember what we called this number 12. What was this? Well, this was called the quotient, right? Because we were taking 25 and we're going to divide it by 2. So this was called, we called this the division algorithm. And so now what I'm going to do is I'm going to repeat. I'm going to take this number 12 and I'm going to put it over here. And then what I'm going to do is I'm going to divide that by 2. So when I divide that by 2, what do I get? Well, I get 2 times 6, and there is no remainder. So we'll put plus 0. So once again, I want to pay attention to this quotient and the remainder. And I'm going to take this number 6, which was the quotient, and I'm going to repeat the process with it. So what is 6? Well, 6 is 2 times 3. And what is the remainder here? Well, the remainder here is once again 0. So I'm going to keep repeating this until I can't do it anymore. But before I go, does anybody have a question about what I'm doing?
No, we're good.
All right, so okay, so once again, the algorithm we want to do is we want to now take that divisor, quotient, and I'm going to take it and play the game again. So now it's 3. How many times does 2 go into 3? Well, it goes in 1 time, plus a remainder of 1. Now, the question is, can I play the game anymore? Yes or no? If yes, how do I play it? If no, why? Does anybody have a comment or a question about sort of what I'm doing here? Did I make any mistakes in this pattern that I'm doing? All right, well, let's ask ourselves, and by the way, I can technically, if I want to keep the pattern up, I could play the game again, because now what was the quotient? The quotient was 1. So you say, how many times does 2 go into 1? Well, the answer is 0, but there's a remainder of 1. And so the observation then is look at the remainders. And you need to think about why this is true. But if you look at these remainders, is the remainders are 1, 0, 0, 1, 1. And so this is the binary or base 2 representation of 25. Yes or no? So what I want you to think about is think about what we're doing here. And then notice and compare, take your mind back to Monday, what we did. On Monday, we started with them points, those dots. We went and moved right to left. And so really the correct way is to reverse the direction. And so we reverse. And when we reverse, what do we obtain? We obtain that 25, and let's be very clear, in base 10 is equal to 1, 1, 0, 0, 1, and that's in base 2.
The ones are wrong.
What do you mean the ones are wrong?
You have 1 0 0 1 wait 1 0 0 1 1. You have 1 1 0 0 1.
Right. Did you not read what I wrote above it? We
Oh my God.
Now the question for you is to understand why we're reversing it. And then also to understand why this works. So why does this work? Well, let's maybe write this out a different way, and then we're going to have to move on, because we can't spend an eternity talking about this. It's just one of those things that you guys have to sort of play around with and understand why it works. So what I'd like to do now is I'd like to write this line of reasoning, but I want to write it differently. Remember, we want to think of these as powers. These are the coefficients if we write 25 as powers of 2. So let's write this from another perspective. Let's say 25 is 2 times 24 plus 1, right? Now instead of writing 24, let's write 24 as 2 times 12. And then it would be plus 0. We'll write that in just for... So maybe I'll use a different color here. So instead of writing 24, I'm going to think of this as 2 times 12 plus 0. And then I'm going to do the same thing again. So if I play the game again, and instead of writing 12, what I'm going to write is I'm going to write 2 times the quantity 2. Now replace 12. What is 12? Well, 12 is 2 times 6. And then, of course, it's plus 0 plus 0. So I'll leave that alone. Plus 1. And then what is 6? Well, maybe we clean this up for a second. Maybe we clean this up as this is 2 to the power 3 times 6. And then this is plus 1. And then now we replace 6. What's 6? Divide by 6. 6 by 2, excuse me. Then this becomes 2 times 3 plus 1. And then, of course, this becomes 2 to the 4th times 3 plus 1. And then what is 3? Well, we already know what 3 is. It's 2 times 1 plus 1 plus 1. And then I'm running out of space, so I'm going to come up here. So this, if you do just multiply through, you get 2 to the 5th plus 2 to the 4th. But the problem is we don't want 2 to the 5th. So first, okay, let me hold on a second. Let me backtrack before I say something that's incorrect.
I'm confused.
All right, let me backtrack. What are you confused about exactly?
Why did you do 2 to the 5th plus 2 to the...
All right, let's backtrack for a second, all right?
Okay.
Do you follow me up to here?
Yeah, that's all good.
All right, good. So now what I'm going to do is I'm going to divide 3 by 2. So what's another way of writing 3? Another way of writing 3 is 2 times 1, right? Because 2 goes into 3 one time, plus 1. Are you with me there?
Yeah, that's good.
All right. Okay, now, what I did before is I took this 2 to the 4th and I distributed it. So I'd have 2, but let's go one more step. Let's think about what we did on the previous page. Now I'm going to, and it might seem silly, but I'm going to write this 1. What is 1? Another way of writing 1 is 2 times 0 plus 1. Now you're going to say that's ridiculous. I get it. And then this is plus 1, and then that's all in parentheses. And then this is plus 1. So what I'm doing is instead of writing it, if you look at the previous page, I'm writing it in like step by step. But what I'm doing in this page is instead of writing it as some sort of process like procedure, I'm just replacing each number with what it's equal to. Okay, now, if we clean up what's inside of here, if we clean this up, you have 2 to the 4th. Now you have 2 times 1 plus 1 plus 1. Do you agree or disagree?
Yeah, that's good.
Which you could argue, well, that's the same thing you had here, O'Grady, right? So at what point, first off, you should not recognize, and this is the second time I went through it, we have an error here, and no one's pointed it out yet. I mean, if you think about this, there's no way what I have over here. What is this? This is 2. So this is 3, right? This is the number 3. 2 to the 4th is 16, correct? So what is wrong with this? 16 times 3 plus 1 ain't 25. So where is the error? Where is the arithmetic error back here? Does anybody see it?
Oh, is it under the red line?
Oh, wait.
You guys, I mean, I wrote this in red and no one has screamed about this yet.
Yeah. Oh, you did the 2.
Oh my God.
Oh.
You got, see, we're finally paying attention.
You guys are all dummies. I found it out.
Yeah. No one is dumb. It's just that here, again, this goes back to the O'Grady philosophy. You guys are so worried about memorizing crap and so worried about what's the answer and so worried about mimicking that you're not thinking. You got to think. So the very first line is an F up, right? So this doesn't make sense. The last I checked, 2 times 24 plus 1 ain't 25. Look at this. I could have been clear as day. I put it in red. Okay, lesson learned, right? So let's think. You should be asking yourself at each step, does it make sense? So anyhow, let's take, well, let's not erase it. Let's make sure it's there so everybody remembers the lesson of the day. Boom, boom, and let's move to the next page. And we'll repeat the fun. So anyhow, let's try again. Second attempt. This is called learning. We often make mistakes. Don't let people fool you. 25. It ain't 2 times 24. It's 2 times 12 plus 1. Now, what is 12? 12 divided by 2 is 2 times 6. And then this is plus 1. And then what is 6? Well, 6 is 2 times 3 plus 1. So we can sort of clean this up if we'd like. How many copies of 2 do I have? I have 2, 2, 2. So that's 2 to the third, which is 8, times 3 plus 1. So this is still correct. Oy vey. Now, what is 3? 3, if you'd like, is 2 times 1 plus 1. And okay, so then if I distribute this 2 to the power 3, this is 2 to the fourth plus 2 to the third plus 1, which we can finally write out as 1 times 2 to the fourth plus 1 times 2 cubed plus 0 times 2 squared plus 0 times 2 to the power 1 plus 1 times 2 to the power 0. And
Wait,
so now,
how do you do 2 to the fourth and 2 to the third?
how did I get them?
Yeah.
Distribute this. What's 2 to the third times 2? 2 to the fourth. What's 2 to the third times 1? 2 to the third.
Oh.
That damn distributive law, it'll get you. And so look at the coefficients now. 1, 1, 0, 0, 1. Which is exactly, if you go 2 pages back, what we got. 1, 1, 0, 0, 1. All right. So what you need to do is you need to have a come to your brain moment with why that algorithm we did 2 pages ago works. And then if you know a little bit about programming, and like I said, I'll share this, you can write a very simple while loop or a for loop to do this. It's very straightforward. All right. Any questions about this? That was good. We had a nice little.
That was fun.
That was, well. All right. So there you go. That's one way that you can convert. Again, this is the quickest way to do it, just to do it, would be to do this sort of reasoning. But the brute force way, which we did here, this is the brute force way that you could do. This is equivalent to the dot method we did. This is a very easy procedure to have a computer do for you, and a computer will do this for you instantly. And of course, probably the most efficient way to do it is go to the internet and you just tell the Google machine 25 in base 2, and it's going to spit it out 11001. but you should understand how to do this. So, like for example, if I ask you this on the homework, I am not asking for you just to tell me the answer. That proves nothing. What, you're good at Google search? I want to know how you did it. So keep that in mind. All right, any questions? Okay, so the next problem on the homework was to go the other way. Take a base 2 number and write it in base 10. So, for example, let's take, so this will be problem 2. Convert, how about 101101 to base 10. So what does this mean? Well, we talked about this yesterday. This means, let's look at the powers here. How many powers are we going to have? 1, 2, 3, 4, 5, 6. So the 0 through 5. 0 power, first power, second power, third power, fourth, fifth. So this means 1 times 2 to the 5th plus 0 times 2 to the 4th plus 1 times 2 cubed plus 1 times 2 to the 2nd plus 0 times 2 to the 1st plus 1 times 2 to the 0. So we remember we had a learning moment with this on Monday where we started writing this crap out correctly or incorrectly. So this is what base 2 means. These numbers are the coefficients of the powers of 2. So now we just have to do normal arithmetic. This is 2 to the power 5. Well, 2 to the power 4 is 16. So this is 32 plus 0 plus 8 plus 4 plus 0 plus 1. And then, of course, if you do the math, this is 44.
Isn't it 45?
I don't know. You tell me.
32 plus 8.
Yeah, I know. I forgot. This was an honest mistake. I didn't do that on purpose. I forgot the 1. You're correct. But you learned, right? So you understand, you're following along, correct?
Yeah, this is very enlightening today.
It is. That's how you learn. Learning's fun. There's one thing I can convince you fools of, and I say fool in the most loving way, and you know this. You got to stop trying to be mimicking procedures. You need to understand why they work, not mimic them. That's all I ask. Now, by the way, we can verify this. How do we know we got the answer correct? Well, one way to check that we got the answer correct is we can say 45 in base 2. And we get 101101. And I believe that's exactly what I gave us. 10, 11, 1. Let's see. Yep. 10, 11, 0, 1. Yep. So this is correct. Does anybody have a question about this? All right, now problem 3 is very similar to problem 1. You can do it in any way. You just want to divide by 8 instead of 2. Does that make sense? So base 8 means you ask about what happens when you divide by 8. So let's do one real quick. So let's take, I don't know, how about 55 in base 10 to base 8. So 55, one way to think about this is 55 equals 8. How many times does 8 go into 55? Well, 8 times 5 is 40. 8 times 6 is 48. 8 times 7 is... So you understand where I'm heading with this? So again, 8 times 6 is 48, so it goes in maybe 6 times plus what's the remainder? Well, the remainder would be 7. And then you play the game again. So can you write, so remember, our job is to write this as powers of 8. So what does this become? Well, one way to think about this is 6 times 8 to the power 1 plus 7 times 8 to the power 0. So this in base 8 would be 67. So that might be a little more tricky for you to come sort of come to terms with. So if you have a question, please ask. Did we make any errors? Any questions, comments? Very good. All right, moving on. Problem 4 was asking you to do a proof. I'll do one of the two for you to show you how this goes. So we'll do part A. So we want to prove that if A divides B and A divides C, then A divides the sum of B plus C. So how do you prove this? Well, one way to think about it is by assumption, there exists K in the integers and J in the integers such that, what does it mean for A to divide B? Well, that means that A times K equals B and A times J equals C. So what our job is to do, that's our assumption, that's our if part. We need to show the conclusion is true. That's how we do a proof in this manner. And so now you just need to show that there's some integer times A that's equal to B plus C. Well, there's not much to this. So note that K plus J is an integer. And that A times K plus A times J by the distributive property of integers is the same thing as A times K plus J. And maybe that sounds funny. Let me put a period here because that's sort of sounds funny. So let's write it a little differently. So since AK plus AJ is equal to this and AK plus AJ is equal to B plus C, we conclude that A times K plus J equals B plus C. Hence, A divides B plus C. Should put that in parentheses. By the way, when's the due date for this? Did I say it tonight? Because you don't have to turn it in tonight. If you need more time, please take the weekend or whatever.
Yeah, it's due tonight.
Hey, you don't have to turn it in tonight.
Thank you.
All right, so that was problem 4. 5 is, these are just finding remainders. So let's note this. For 5, if I write A mod n, that just means the remainder when A is divided by n. So for example, if I have 28 mod 5, that is equal to, well, take 5 and divide it into 8. It goes in 5 times with a remainder of 3. So this is equal to 3 since 28 is equal to 5 times 5 plus 3. So this is the key thing, the remainder. Does that make sense? Any questions about that? This is so much fun. All right, so yeah, problem 5 is pretty straightforward. And by the way, again, you should think about these as the division algorithm. That's the bigger picture. That's what helps us with the applications. Okay, so number 6 is an important thing. So before we do number 6, so in the normal, and I'll put normal in quotations because what does that mean? So in normal, say algebra, we have what's called a cancellation law. And you used it all the time, and you still use it. So what you have is you have if A times B equals A times C, then you can divide out the A. Then you could say B is equal to C when, of course, A is non-zero. So the way you might have thought about this is how you solved equations when you were a little kid and even now. So this is how, or this is why you can basic equations. Like if you had 5x equals, say really anything. Let's say 25 times 3. Well, what can you conclude? Well, you get that x is equal to 15. And more generally, you had this following result. and this is another thing that you use. More generally, you had if two things are equal, if A equals B, then A times C would equal B times C. So that's sort of the other reasoning. So these are basic sort of facts about numbers that you've used since you learned algebra. The thing is they don't necessarily hold when we're doing modular arithmetic. So just because it's true when we're allowing all real numbers doesn't mean it's true when we're allowing only numbers modular some integer. So the way I stated the problem is, make sure I get them. I used A, C, E congruent to B, C. So I had AC congruent to BC mod n. This does not imply that A is congruent to B mod n. And what I asked you to do is to find a counterexample, find where this fails. So that's basically, you got to do some trial and error. So we need one. Well, let's look at how this might go about. What does this mean? What does AC congruent to BC mod n mean? So it helps to know what this means. This means that n divides AC minus BC. And what does A congruent to B mod n mean? That means n divides A minus B. So what you need to do is you need to find three numbers, A, B, and C, so that this is true, but this is false. So maybe you can ponder that for a while. Does anybody have a question, comment? When would the top one be true, but the bottom one be false? Well, one way to think about it is choose. I mean, I don't want to steal the fun because maybe some of you actually care to discover this on your own. But if you just think and reason algebraically, choose C a multiple of n, and A minus B not one. So for example, here's one you could do. Let's say n is 3. N is 3. Let's say C equals 9. And let A equal 2, B equal 1. So let's try it. So does 3 divide 18 minus 9? And the answer is yes. Does 3 divide 2 minus 1? And the answer is no. So there you go. There's one example. Now find one different than that. I mean, I pretty much gave the problem away. Does anybody have a comment, question about this? All right, let me give you a hint for 7 then. So 7 says if you have an odd integer that's positive, then n squared minus 1 is divisible by 8. So for 7, you need to prove, so here's what you assume. You assume n odd. So that means n equals 2k plus 1 for some k. And then what do you need to prove? Need to prove that n squared is congruent to 1 mod, what was it? 8? Forget already. Mod 8, yeah. Now, oftentimes it's a little easier to rewrite this in a more familiar language. That means that 8 divides n squared minus 1. And another way to write that is that if 8 divides it, that means that 8 times j is equal to n squared minus 1 for some j. So can you show n squared minus 1 is equal to 8 times an integer? So take n, square it, and see what you can do. There's a couple ways you might reason here. I'll let you think about it. It's not easy, but once you see how it works, you're like, oh, that wasn't bad. Any comments, questions about this fiasco? All right. Let's go to the next one. The last one is probably the easiest one of them. Not the easiest, but it's the most mindless one of them all. It's just you don't know that yet because you probably don't know what we're asking you to do. So for 8, we want addition and multiplication tables for z something. And so instead of doing z5, I'll do z3 so you can generalize it. What is z3? Well, it's these integers, the integers less than 3 that are positive. So what do we mean by addition and multiplication tables? Well, so let's make a table. I'm going to put the values of this up here, and then I'll put them down here. Oh yeah, hold on one second, guys. We have a request from the child. Yes, honey. All right, we're back. So, oh, here's paper, honey. Here, sweetheart. There you go, honey. So one way to think about this is you want to ask yourself what happens when you add these numbers. So when I add 0 and 0, normal, I get 0. When I add 0 and 1, 1. So we'll put a plus sign here. When I add 0 and 2, I get 2. So there's nothing unique about adding 0 and 1 or adding 0 and 2. But what happens when I add 1 and 1? When I add 1 and 1, I get 2. What happens when I add 2 and 1? Well, I get 3. But 3 is not in my set. So what you need to ask is, what is 3 mod 3? Well, the answer is 0 because its remainder is 0. Similarly, when I go here, if I say 2 and 1, I get 2. And then what's 2 and 2 when I add them together? I get 4. Well, what's the remainder when I divide 4 by 3? I get 1. By the way, this is 1 and 2. This is, again, this is incorrect. This should be a 0. So the key thing to note is what we're doing is we're writing out what happens when I add any two numbers in this set together. Well, everything is normal except for this, this, and this, because you would think that this should be. So here's the thing to note. Note, 2 plus 1 is 3. But 3 is what? Well, 3 is congruent to 0 mod 3. So that's why we put the 0 here. And 2 plus 2 is equal to 4, but that is congruent to 1 mod 3. And that's why there's a 1 here. Now, the same thing goes for multiplication. So if I'm going to ask myself what happens when I multiply the numbers of my set to each other, 0 times 0 is 0. I guess I should maybe do this. And there's lots of cool things to be thinking about here. There's lots of symmetry. What's 0 times anything? 0, 0. What's 0 times anything? 0, 0. 1 times 1 is 1. 2 times 1 is 2. 2 times 1 is 2. What's 2 times 2? It's 4, but 4 is congruent to 1. And so the multiplication table looks like this. So this is probably new to you, but what we do is we call these the multiplication and addition tables. And when I asked you to do them for z sub 5, and it's pretty cool. You'll get this beautiful table, and it's an example of some structures that are just, the symmetry is quite fascinating, and you can study that stuff. There's branches of math where people study these things, and it turns out this number system is very useful. As I've alluded to, we use z sub 12 to tell time. So, any comments or questions about this? Going once, going twice. I mean, look, I'm okay. I'll go one further, but I mean, if I go any more, it's still in the fun. So let's do z sub 4. So suppose we wanted to do z sub 4. So what is z sub 4? It's 0, 1, 2, and 3. So if I do the addition, I have 0, 1, 2, and 3. And then I want to know what happens when I add members of this set to each other. So if I add 0 and 0, I get 0. 1 and 0 is 1. 2 and 0 is 2. 3 and 0 is 3. Same thing down this column. I'm just adding each number to 0, so it's itself. Now, this column is what happens when I take this number by this number. Well, I get 2. And then 1 and 2 is 3. And then 1 and 3 is 4. But 4 is not in my set. So I would normally put 4 here. So maybe this will be helpful for what I'm doing. And then over here, 2 and 1 is 3. 1 and 3 is 4. 2 and 2 is 4. 3 and 2 is 5. 3 and 3 is 6. And then 3 and 2 is 5. So here's the thing. What we have to understand is these numbers, this is not in our set. Not in our set, not in our set, not in our set, not in our set, not in our set. But these numbers are congruent to something mod 4. What are they? Well, this is 0. This is 2. I'm sorry, this is 1. Excuse me. This is 1. This is 2. And then this is, of course, 0, 0, 1. So the actual table, the way you would say the addition table for z sub 4 is actually this. So it's 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1. Look at the symmetry here. 3, 0. The patterns. There's patterns everywhere. It's really cool. Yes, sweet. Wow, that's beautiful. Can you draw me another one?
No.
Okay, thank you.
This for you.
Okay, thank you.
Draw a picture for me.
Yeah. Ricky, go draw a picture for them. Does that make sense, Michelle? I mean, again, it's weird. I don't want to pretend this is easy, but what you end up seeing is there's these awesome patterns. And these patterns that are hiding in here, these are what make all these applications super efficient and quite interesting. And here's a cool thing that you would recognize. If you did z sub 4 and then 5, and then you did them all, and you compared ones that had, you know, I know we didn't define it yet, but you guys know the difference between, like, I think most of you know what a prime number is. The tables with primes have different patterns than the other ones. There's so many cool things hiding out in all this. Okay. Speaking of, let's talk about that stuff now. Are we good? Does this make sense? I don't know. Another sort of way you can think about this, Michelle, and whoever else is pondering, is you could think about keep counting in this. If you kept counting, this would be 0, 1, 2, 3, and then this is 4, 5, 6, 7, and then 8, 9, 10, 11, etc. So, for example, in Z4, 11 is 3. Ricky said she made this one for them. That's you guys. There you go.
Ricky, make one for
hi.
Mackenzie.
You want to say hi to everybody? You say hi.
Oh,
You say
Hello.
hi. Say hi. Tell me. Say I need my diaper changed.
I need my diaper.
Ricky, draw me a photo.
Okay, go draw something, Ricky. Okay. Anyhow, welcome to 2020 in the Rona. So look, this is you know, again, don't forget, a lot of what we're doing is we're introducing you to branches of math. So one area this stuff is studied is number theory. Another area, like I suggested, is what's called modern or abstract algebra, where you study these sort of different types of structures. So we're not using the traditional number system. We're using just four numbers. So it's quite interesting. And by the way, there's some connections with this stuff. And then if you drew out, say, the addition and multiplication for, say, z sub 2, you would notice some things with the binary and stuff. So it's really cool, the connections and how things cross over and all that. All right, so what's next then? You know, like we said, why do we care about these congruences, and why do we care about different bases and all that stuff? Well, like I said, there's lots of different reasons one might care, and we're going to give you a little bit of that coming up. But we have to do a little more work first. We have to understand a little bit new things. So if we want to make the most of what we call modular arithmetic, divisibility, and congruence, we need to study what are called prime numbers. So you guys are probably familiar with what a prime. Yes, honey. Is this another one? Ooh, thank you. There you go, guys. There's a good picture. Thank you, Ricky.
Wait, I can't see it.
Is that a rainbow?
No, you gotta put it closer because your green screen is.
Oh, that's right. I have that stupid green screen. There. We'll bring that in on Monday. That'll be my present to you guys. Thank you, Ricky. You draw another one?
Ricky, I'll keep it.
Okay, Ricky, I gotta finish this. All right. Go play on the slide or something. All right. Okay. So, look, it's like some of you have studied chemistry before. Some of you have studied chemistry before, or some other things, other subjects. But chemistry is a good example of how what we end up doing is we sort of study the big picture by looking at what makes the big picture. So in chemistry, we look at like the table of elements, and we think about how things are made up of. For example, water is hydrogen and oxygen. So these, the building blocks of numbers, at least integers, are what we call the prime numbers. So we need to define them. So in many ways, these are the building blocks.
I like it. Can I play with this?
Sure, go ahead, honey.
I want to play with on here. Just look at.
So what do we define? How do we define a prime? So we say a number is prime. I guess we should be more specific because it's not just a number, it's an integer. So we say an integer is prime if it has two divisors. P, or excuse me, I don't want to use P because I didn't define it. Yes,
Her back on. Okay, then. I did it.
so the only way a number can be prime is if it has two divisors, one in itself. So inherent in this is that you can't have negative. Well, I guess let's just write this. So we assume the integer is at least 2. So that saves us from some issues. So you guys are probably familiar with the primes 2, 3, 5, 7, 11, etc. Does anybody have any questions about that?
I lay her down right
Okay,
here.
you lay her down right there.
I can't help. No,
Okay.
no.
All right, hold on.
No,
Ricky, honey.
Lay her.
So the first few primes. What are they? 2, 3, 5, 7, 11, 13, ... Here's an amazing fact, and it's one that I don't know if it's amazing, but it's an important thing to be sure. So there are infinitely many primes. There's no largest prime. So that's something to keep in line, and we could actually prove it, but we're not going to right now. If an integer is not prime, the negation, the not prime, is called composite. So those are two words that you should be familiar with in a class like this, prime and composite. Does anybody have a question about this?
Daddy. Dad, how you play with this? Daddy, how you...
Ricky, you are absolutely adorable.
Yeah.
She said, yeah. Ricky, listen, honey. Ricky, we have 4 minutes left. And then we'll play, I promise. Okay? Oh, you want to put it there? Is that what you want to do? Okay. All right, so here's another cool fact. which will make sure you understand that it's a theorem.
Can I play with
Yes, go ahead. So this is, some of you from calculus will remember a theorem with a similar name. So this is called the fundamental theorem of arithmetic. And what it says is, it says the following.
I can't open this.
Ricky, you're on my nerves, honey. Here, open. There you go. So basically, well, I shouldn't say basically. What it says is a pretty something that it probably was made aware to you when you were in middle school, elementary school, when you were in math class. And it says the following. It says every integer greater than 1 has a unique prime factorization. So let's, instead of thinking about why this is true, let's just look at some examples. You know, take something like boring, like 37. Well, 37 is 5 times 7. That's a prime. Take something like 100. Well, 100 you can think of as 25 times 4, so that's 2 squared times 5 squared. And perhaps some of you did this. Maybe you guys made what we used to call them factor trees when I was a kid in school. Maybe you would have done something like 100. You might have said is, 25 and 4, and then you would have said 5. 25 is 5 times 5, and you'd have said 4 is 2 times 2. So maybe you guys did stuff like that in school.
Did you mean 35?
Oh yeah. I'm sorry. I did mean 35. You talking about over here? Yes, I did. I got ahead of myself. Yeah. That was a mistake. My apologies. That's among 2 mistakes today. And then 1 planned mistake. Not good. The study of primes literally has been going on since the beginning of written history, and it's not even complete. There's all kinds of important questions about primes, but we don't really have time in this class to get to the bottom of it, or even pretend to scratch the surface. But what we do need to do is we need to talk about the sort of properties of primes that are going to be useful to what we have going on right now. So some other things that are important that you are familiar with, I believe. So So we call the largest integer that divides both A and B, the greatest common divisor of A and B. And typically we write it using GCD of A and B. And then another important concept, if we have 2 numbers and their greatest common divisor is 1, we say A and B are relatively prime. And we are a minute over. So what I'll do is I'll stop there. If you have a question, please let me know. Send me email, and then on Monday we can sort of reconvene all this fun stuff. And we'll go from there. Does anybody have a question or comment? Once again, I apologize about not being in person today, and I apologize for Ricky interrupting towards the end.
Don't apologize for Ricky.
I know, but it is what it is. Someone has a question. Question. Yeah, I mean, Michelle, yeah. So the question is, am I changing the date? I'm not going to change it, but you can turn it in whenever. I would never take off points if you turn it in on Monday. Now, if it'll make you feel better, I can officially change the due date. But I'll put it to you this way, Michelle, I ain't grading this homework for at least a week. So you have until then to get it in. So does anybody else have any questions, comments? All right, well, listen, guys, I know this is kind of overwhelming. What's that? Say that again.
Draw me a picture.
Did I draw you a picture?
And Ricky draw me a picture.
Yeah, I'll bring those in. She'll make you guys artwork. Regular Picasso over here.
Yay.
Yeah. All right, well, listen, guys, I know this stuff's a little overwhelming, so you just got to be positive that you can get it done. And then, you know, I know you guys are under a lot, especially with the semester ending. So be positive. You have a few more weeks of suffering, and then you have a break. All right, guys. Thank you very much. Take care. I will see you Monday, if not sooner. Well, Anthony, I'll see you in an hour. Or no, 15 minutes. Oh, my God. I'm losing my mind. Take care, guys.